Hi, my name is McCoskey. I'm here to talk about my idea for a rotary engine. What you see before you is one set up to maybe drive a helicopter, maybe a quadcopter. I want to get inside this engine and try to show you how it works. Let's start with the most basic elements. The round rotating thing I call a paddle, and then we have a fuel injector and a spark plug. As the paddle goes by the fuel injector and the spark plug, the fuel injector injects a little fuel and the spark plug fires, and that ignites a small flame. But it doesn't do much good without something to contain it. Here we have added 2 combustion chambers, 2 rotating plates, and 2 valves. The rotary engine we're describing here would probably have to be 2 to 3 times as large as a piston engine to get the same power. That's, I believe, the main drawback of this type of design. But I also think that the other advantages of this type of design make it worthwhile to at least investigate it to see how it might work. The piston engine gets its power density, by compression. The piston engine has a compression ratio of about 10 to 1. So you might think that would mean that the piston engine would be 10 times more power dense than the rotary engine. But all things considered, it doesn't work out that way. 2 to 3, I think, is a reasonable first guess. The rotary engine is under power for about 75% of the time, whereas the piston engine is under power for a little under 25% of the time. Unlike the piston engine, the rotary engine can be designed to be under power for a different percentage of the cycle. So that's a design trade-off that would probably need to be explored. On the other hand, the rotary engine has a much better power-to-weight ratio than the piston engine does. The piston engine has to deal with pressure of about 1,500 pounds per square inch, while the rotary engine has to deal with pressures of only about 150 pounds per square inch. So the piston engine has to be really robust, and which means bigger and heavier components. So on that basis, you might think that the rotary engine has a power-to-weight ratio advantage over the piston engine. Now, I'm not sure how that would exactly work out under good engineering calculations, but it would be, I think, a lot more power-to-weight ratio than the piston engine has. Also, the rotary engine should have a much better fuel economy than the piston engine. When the exhaust valve opens on the piston engine at the end of the power stroke, there's still approximately 150 pounds of pressure, 150 pounds per square inch in that cylinder, which causes a loud pop. The rotary engine doesn't do that. When it opens that exhaust valve, the pressure inside the combustion chamber is about equal to atmospheric pressure, so there's no pop and no muffler needed. Not only does the release of that 150 pounds of air pressure into the atmosphere indicate a waste of energy, the back pressure caused by the muffler further decreases the efficiency of the piston engine. Another factor that affects the usability and longevity of an engine is vibration. Any engine that gets its energy from exploding gases is going to vibrate. But the reciprocating piston engine adds unnecessary vibration because of the reciprocation. The worst offenders are the pistons and the rods, because they're heavy. Vibration causes increased load on the bearings and increases friction. It also makes the mounting of the engine a bigger engineering challenge. An engine that produces less vibration can run at a higher rate of speed, more RPM revolutions per minute. An engine that runs at a higher RPM has effectively higher power density. So that would probably offset some of the power density advantage of the high compression piston engine. Another important factor in the success of a commercial product is cost to manufacture. I believe that the cost to manufacture of this engine would be dramatically lower than the cost to manufacture of a piston engine. The rotary engine would use lighter and lower cost parts. The tolerances required would not be quite so tight, and the lighter parts would be much easier to assemble. One final factor is fuel additives. The rotary engine wouldn't require any fuel additives. If the fuel exploded before the spark plug fired, it would have little or no effect on the rotary engine. The political and environmental issues around fuel additives mean that the market for gasoline is balkanized both in time and space. We have different additive mixes for winter and summer, and we also have different additive mixes for different regions of the country. If that were all eliminated, if we just had one kind of fuel, then the price of gasoline would be cheaper than it is now. By adding 2 more plates and 3 more panels, we can get an engine in a square 8 configuration. The engine has 4 paddles and 8 combustion chambers. An advantage of this configuration is that the engine doesn't need a starter. 2 of the paddles will always be in position where they can be started by simply injecting some fuel and firing the spark plug. That also means that the engine wouldn't have to be left idling to be instantly available for rotation. Here's a look at the mechanical linkages that synchronize all these components and transmit power to the output shaft. I guess there's a lot of ways you could do this. You could do it with chains, you could do it with belts, but I guess gears are probably the simplest and most reliable. If you have questions or comments, or you'd like to get involved in this project, my email address is mckyyy@gmail.com.